Hey everyone, it's Mr. Canfield. Today we're going to be doing chapter 4-5 in geometry. So if you go down to today's Schoology folder, you'll see everything you need is here. You can print stuff out. You can write on your screen if you're using your Chromebook, or take your own notes on your own paper, whatever you need. Today's lesson is pretty short, but we start with a warm-up with an interactive app to use online. So we're looking at SSA, and we frequently say ASS because it reminds us that there's something that's not right about that because you're not supposed to be using that word in school. So when we have that, what's going on is we've got an angle down here that's locked in place. We've got a side that's locked in place, and we've got another side that's locked in place in that order, ASS. And it's possible that you have everything and you don't have a triangle, which is fine. That's something that's super normal. But what if I make it into a triangle? And feel free to play around with this yourself. Make it into a triangle, see what happens. All the other triangle congruency theorems that we've looked at so far, when you have the given information in the acronym like SSS, ASA, SAS, all those, you're locked in and there's only one possible triangle. But with ASS, or SSA to be more appropriate, all of a sudden, instead of having a single triangle, there's actually two possible triangles. That kind of dangling end there could make this triangle over here or this triangle over here. Both of them would have a side of 5.4. So because of that, that is why angle side side is not okay. There is one possible situation where we can get this to work. And it's when, let's see if I can get it. Boom. Boom. When that dangling side can only reach straight down and touch just once. And that's when it hits at a right angle. So in here, what are the three possible situations? You could have one triangle, two triangles, or three triangles, or one triangle, two triangles, or no triangles at all. Those are the three possibilities. And SSA is not allowed because we are not sure which of those three it is when that's locked in. So because of that, we say it's ambiguous. That word right there, ambiguous. So, all right. I hope that was helpful for your warm-up. Now on to our actual Schoology, or not Schoology, our written out lesson. So there's a special theorem that we're going to be dealing with today, and it does go back to what happened here. That straight down here, that one I'm making what's called a right angle, a 90-degree angle. It's a right triangle. So there's something special with right triangles. And if we label these sides A, B, and C, which is traditionally how it's done, the only one of these that really matters is C. A and B are interchangeable, but C is a special side. C is called the hypotenuse, the hypotenuse. If you're trying to pronounce it, you'd say hi, then you'd say pa, then you'd say N, and you go oos. So you say hypotenuse. That's how we pronounce it. So a couple key things about the hypotenuse. It's always the longest side in a right triangle. And additionally, if you look at the right angle, the box, it's always across the street from the box. So that'll always be the case. Hypotenuse is always across the street from the box. It's always the longest one. A and B are just called legs. So A's a leg, B's a leg. These are important words, and we will be using them today, so that's why I'm talking about them now. Okay, so Pythagorean Theorem. This is only true for right triangles. You might want to emphasize that in your own notes. This is only true for right triangles. This is not true elsewhere, but every time you have a right triangle, it's always true. In a right triangle, every time you have this. A squared plus B squared is always equal to C squared. So let's break down what this means really quick. In any right triangle, one leg, however long it is, square that. The other leg, square it. Add them together. That's going to equal to what you get when you square the last side. So here's an example. I'll just draw some random looking right triangle. Whoa, it's so different looking. I'm going to put a 3. I'm going to put a 3 here, and I'm going to put a 4 here. And I'm going to say find the third side. And right now, you can't. We don't know it's a right triangle. What if that's an 89-degree angle? I don't know. Okay, so now the problem is completed. I can say, okay, find the third side. So if I was going to do that, all I need to do, well, 3 and 4 are my legs because they're touching the right angle. So I could say 3 squared plus 4 squared is going to be equal to whatever my third side is squared. Well, okay. Well, what's 3 squared? Ask yourself that. Just think in your brain, what's 3 squared? And you got a few options. Your brain might go, I don't know, and that's fine. Your brain might go 6, and that's fine. Those both mean you need a calculator. 3 squared means 3 times 3 times itself. So 3 squared is 9. You can do the same thing with 4. If you get 8, be careful. It's actually 16. So 9 plus 16, that is going to be equal to whatever the heck our third side is when you square it. So, well, let's see. 9 plus 16 is 25. And so our third side, when you square it, you get 25. Well, if you're not sure what that is, you can always go to your calculator. And a way to undo squaring and actually find out where it came from. Wait, where's my calculator? I click, it's open. Oh, weird, it's over on my other monitor for some reason. Okay. So if you want, you could say 25 and take the square root of it, which is that guy right there, 5, right? Because 5 times 5 is 25. So C is equal to 5. So this is a 3, 4, 5 triangle, and we'll learn more about these later, but this is called a Pythagorean, just the name, Pythagorean triple, because you get nice numbers, nice whole numbers. It's rare to get nice whole numbers in right triangles. 99% of the time, you get awful numbers for at least one of the sides. So if I picked 2 random numbers here, the third number is not going to be nice. I picked 3 and 4 because I know 3, 4, 5 turns out nice. A little bit of extra bonus information that you don't actually need. All right, let's keep going. So let's look at these 2 triangles, and are they congruent? Let's see. Well, if I look at what I have an angle and then a side and then a side. Wait. In that order. Angle, then side, then side. That's SSA. Side, then angle. Angle, then side, then side. We've said that's a no-go. And that's still true. But. Check it out. We've got this side here, some unknown side, and then this side here. The other triangle is in the exact same setup. And since it's a right triangle, I could use the Pythagorean Theorem and say this squared plus this squared gets me my third side squared. We could go through, we can do some solving. We could actually find out what this is because we know the other 2. And since we know the other 2, we can say, well, this is going to be some third length. And it's okay if it winds up equaling this side. It's not a big deal. But it's some length that's locked in by these 2. And additionally, over here, since it's the same setup, this is that same locked in side. Whatever that one is, this one's the same. And now, sure, we had SSA, which was illegal, but now we have side, side, side. And so the Pythagorean Theorem lets us, in right triangles only, lets us turn ASS into side, side, side. And because of that, we have a special name for this. If you have this setup where you got the right angle and one of the legs and the hypotenuse, We call this the HL congruence. H stands for hypotenuse, L stands for leg. If they have the hypotenuse and a leg, boom, we're good. So none of that SSA business. HL, that's what we use. So let's go. This is the definition as the book gives us. You can read it in the PDF if you want the detailed wordy version, but that's the basics of what I told you. So check this out. What information would be sufficient to show that the triangles are congruent by the HL theorem? So here we got one of the legs. We got the hypotenuse. Let's look at the other triangle. Let's see. Here's the right angle. So there's the hypotenuse. Oh, we just need one of the legs then, right? So that's 6. We just need one of these two sides to be 6. There. Now they're congruent. So if we had that, we'd have HL. And if you're like, Canfield, that's kind of easy. Yeah, that's all. That's all this is. So we can use HL to solve some difficult questions. So this is going to be an example of a proof. I will not require you to do these on tests. I just want you to be exposed to them. So check this out. We've got all this information here, and we're trying to show that ABC is an isosceles triangle. And ABC is, let's see, A to B to C, this triangle. We're trying to show this triangle is isosceles. And if you remember, isosceles means that 2 of the sides are congruent. And that also implies then that these 2 angles are congruent. So that's our end goal here. And you might be like, yeah, they're obviously congruent to each other. This is so obvious. Here's the thing. Just because something looks obvious doesn't mean it's actually true. So there's a famous video online where this guy takes a bar of chocolate, and it's all these squares, and he cuts one of the squares out of the chocolate, puts it all back together, like he cuts it up funny and pulls a square out, puts it all back together, and it's the same bar of chocolate. And he magically got an extra square of chocolate. That's not a magic. He didn't do anything magical. He actually made the bar of chocolate smaller. It's just hard for us to see it. So there's a chance that even though this looks like perfectly equal on both sides, there's a chance that it's slightly off and we just don't realize it. So what we can do in using the things that we've learned in geometry is we can prove that this has to actually be what it looks like it is. So I'm going to start out, and I see I have a side here and a right angle here. So I'm going to look at these 2 triangles right here. I'm going to look at this one and this one. So these are both right triangles, and they share, so they have a right angle, they have that in common, then they have an equal side in common, and then they have this overlapping side here in the middle in common. So if we're careful, we can see we have angle, side, oh, no, can't do that. Oh, but it's a right triangle. I've got a leg and the hypotenuse, a leg and the hypotenuse. So by HL, HL shows that triangle AEF is congruent to triangle ADF. And if you were like, yeah, they're obviously the same, that's great. But again, if they were slightly off, there's no way they're slightly off now. This is a proof that they have to be the same. So, all right, let's see what's next. So if those are all the same, then that means that this side right here and this side right there are also the same. So that's what it means for triangles to be congruent. And so now I'm actually going to shift our focus down to these bottom triangles down here. And specifically, let's look at the angles here. I wonder what these angles are. Well, think about it real quick. You got a straight line. You got a right angle on one side. What do these guys add up to? 180, right? So that means that if this is 90, this has to be the other 90. So this is also a right angle, also a right angle. And so again, if we're just focusing on these bottom triangles down here, we can see that we've got a right angle that they share. We got that triple dash that they share. We got the double dash that they share. And look, one of them's touching the right angle, so it's a leg. One of them's across, so it's a hypotenuse. So we got hypotenuse leg congruency down here. These two triangles down here are the same. So we could say, like, I'll say this green side right here is the same as this green side right here. So all that means is, well, then this right here is made up of a dashed side and a green side. This right here is made up of a dashed side and a green side. Those two have to be the same length then. And that's what you need to have an isosceles triangle. Okay. What's the big deal? The big deal is we just essentially did what we would need to do in a courtroom to prove something true. In a courtroom, it's not enough to say, he's obviously guilty. No, you have to show beyond a shadow of a doubt, that beyond a reasonable doubt, that he's guilty. And here, to show this was isosceles, we needed to prove to ourselves, hey, there's no chance it's anything but these triangles are equal, these triangles are equal, so those sides have to be equal to each other. And if you're like, that's neat, cool. There's a whole study that you can do in math where you prove things and you see this must be true. It's not a real world thing. It's a theoretical thing. It's a thinking outside the box thing. And it can be a lot of fun. They're like puzzles. And if you hate this, don't worry. We don't do a lot of these in this class. So I'm running a little bit short on time. This one right here, it's another interesting problem. If you are interested, I would encourage you to see if you can kind of tease out why this does have to be true. And this is all the information that was necessary to be given to us to prove that it's true. I would encourage you to see if you can walk through the steps that would guarantee it has to be true. Because, right now I could be like, well, hey, maybe LKM. Maybe LKM is not the same as JKM. Maybe they just kind of look the same right now. So great question for you to try if you want. And that's it for the lesson. If you go in to the assignment folder, you'll see that we have the notes, an exit ticket. So do try the exit ticket. And to get credit for doing this assignment, for doing this lesson, you can email me your answers to the exit ticket, and I'll let you know if you got to fix anything or whatever. And then the homework is here. I'll be checking that in the near future. So it's all there. Hope this was helpful, and I will see you later. Bye.